What mysterious force limits Earth from having mountains taller than 10,000 meters? In the vast solar system, almost all rocky planets have mountains that exceed this 10,000-meter threshold. For example, Mars's Olympus Mons rises to 21,900 meters, and Rhea Silvia Mons on the asteroid Vesta soars even higher, 22,500 meters, piercing the clouds at nearly 3 times the height of Mount Everest. But why, then, are Earth's mountains, on a much larger planet, so comparatively small? We often regard Mount Everest's height of 8,848.18 meters as legendary, yet few know the secret behind that number. It's actually measured from the shoulders of a giant, the Tibetan Plateau. If measured directly from a mountain's base to its peak, Everest's true vertical height is only about 3,484 meters. In contrast, Hawaii's Mauna Loa volcano, measured from its base deep beneath the ocean to its summit, exceeds 10,000 meters in height. However, since 90% of Mauna Loa's mass lies submerged beneath the Pacific Ocean, Everest retains its title as the highest mountain above sea level. Even more surprising, if we measure by distance from Earth's center, Ecuador's Mount Chimborazo actually stands over 2,000 meters higher than Everest. Scientists, however, universally adopt elevation above sea level as the standard measurement, using the average sea level as 0 altitude. This is because Earth has an insurmountable height limit, a natural ceiling set by its own immense gravity. As the most massive rocky planet in the solar system, Earth's strong gravitational pull places tremendous pressure on mountain bases. Rocks can only withstand a limited amount of compression. When a mountain's height nears the upper limit, the rocks at its base begin to collapse like a stack of overburdened blocks. Calculations show that the pressure beneath Everest is already close to the critical strength of rock. If a mountain exceeded 10,000 meters, its sheer weight would cause plastic deformation, eventually making it crumble and sink under its own mass. Besides gravity and rock strength, Earth's dynamic geological activity also continuously lowers mountain heights. Weathering, glacial erosion, and earthquakes act like endless sculpting knives, persistently carving the peaks down. Moreover, Earth's crust isn't a solid iron plate. It's a continental layer only about 40 kilometers thick, floating atop the mantle like wood on water. The higher a mountain rises, the more its underlying crust is pushed into the mantle. This isostatic balance effect gradually consumes a mountain's height over time. In comparison, Mars's gravity is only about 1/3 of Earth's. This means the rocks there experience much less pressure, allowing Olympus Mons to grow and remain stable for over 2 billion years. On the other extreme, on white dwarf stars, where gravity is unimaginably strong, the tallest mountains may be less than 1 meter high. Geologists speculate that around 10 million years ago, Mount Everest might once have exceeded 12,000 meters in height. But under the constant influence of gravity and geological erosion, it has since been reduced to its current 8,848 meters. Even though Everest still grows by about 0.3 centimeters each year, breaking through the 10,000-meter barrier remains a distant, unreachable dream.